Hello everyone. In this video I would like to show you how to create a Streeter-Phelps model for a stream using OpenHydroQual. Here are all the information that we need for the model. Let me just go through this. Basically we have a stream segment with a length of 20 kilometers. I'm going to actually discretize this into 20 segments, 20 elements, each of them with a length of 1,000 meters or 1 kilometer. The properties of the stream are given here. So we have the slope being slope is 0.0001. The side slope of the channel cross section is assumed to be trapezoidal with a side slope of 2. Here is the cross section. Basically bottom width is assumed to be 10 meters, and the Manning's roughness coefficient of the channel is assumed to be 0.035. I'm going to first, basically I'm going to model the hydraulics and then also the reactive transport of dissolved oxygen and BOD. So as our basically upstream boundary condition, we have a flow rate of constant flow rate equal to 540,000 cubic meters per day. The dissolved oxygen concentration is 7.09 milligrams per liter, and the BOD concentration upstream is 16.66 milligrams per liter. Basically, I'm going to use a fixed head boundary condition for the downstream with an elevation of minus 3.9 meters. That means 3.9 meters below the bottom elevation of the upstream boundary. And then the Streeter-Phelps model, actually if I want to write it in form of basically ODE, ordinary differential equation for a batch system, can be written like something like this. So the BOD is being removed through a first order reaction with a rate coefficient of k sub d. I'm also going to assume that we have BOD settling with a rate coefficient of k sub s, and then the DO, for the DO we have, of course, the DO uptake due to the BOD mineralization, and then also basically aeration with a rate coefficient of k sub a. And then this DO sub S is, of course, the saturation oxygen concentration. The parameters that we need for this are provided here. So the BOD decay rate, I'm gonna assume it's gonna be 0.764 per day. This BOD settling rate is gonna be 0.514 per day, and then the saturation oxygen concentration, I'm gonna use 9.092. And I'm going to use an aeration rate coefficient, that means k sub a, of 1.902 per day. So let's get it started. So the first thing what I'm going to do is that I'm going to add 2 plugins that I'm going to need for this exercise. The first plugin that I'm going to add is the Open Channel plugin. So that's to create a model of the trapezoidal channel. So let me do that, and then I am also going to add this plugin called mass transfer, and I'm gonna need this for basically including aeration to the model. So okay, so now I got the plugins added. So now the first thing I'm going to do is that I will add the constituents, the chemical constituents, and then I will add the reactions, and I'll also add the aeration process. So let me first add the chemical constituents. So I'm going to use, this is the icon for chemical constituents, so I'm going to add 2 chemical constituents, and then I can go to Object Browser and click on each of the constituents. Then I'm going to rename them. The first one I'm going to rename to DO, dissolved oxygen, and the second one I'm going to rename it to BOD. Okay, so that's that's it. Then what I'm going to do is that I want to add the reactions, but before adding the reactions, I want to define some reaction parameters that will help me in defining the reactions. So I'm going to add, basically I have two reaction parameters here. The first reaction parameter is going to be K sub D, and the second one is going to be K sub S. So let me call this K sub D. I'm going to use lowercase, and I'm going to use underscore for subscript. And the value of K sub D is 0.764. So 0.764. We can include the temperature effect in OpenHydroQual, but I'm just gonna, for sake of simplicity, I'm just gonna not do that. And then so our second reaction parameter is the settling rate, which is K sub S, and the value for that is 0.514. So this is going to be 0.514. So now I have the two reaction parameters, and I have the two constituents. Now I'm going to go ahead and add the reactions. So basically I'm going to have two reactions. The first reaction is going to be BOD mineralization. I'm going to just use BOD decay. And so basically the rate expression, we're going to use the monode kinetics. As you can see, oh yeah, actually it's going to be the first order decay of BOD. So basically the rate is going to be K sub D times BOD. The stoichiometric constant for DO is going to be -1 because it's going to be used, and the stoichiometric constant for the BOD is also going to be -1. So that's the BOD decay. My second reaction is the settling of BOD, which we're going to also model as a first order reaction. So this is, I'm going to call this settling. The rate is going to be K sub S times BOD. And then the stoichiometric for DO, the settling is not going to consume any oxygen, so the stoichiometric constant for DO is going to be 0, but then the stoichiometric constant for BOD is going to be -1. So that takes care of the reactions. So we have the two reactions now. Then the next thing I'm going to do is I want to add the aeration process. So aeration is basically, this is I'm going to use this thing called atmospheric exchange to model aeration. So so I'm going to click on this one and create one. It's going to go under sources because, you know, aeration is actually a source of a chemical. So basically I'm going to call this aeration, and the rate of aeration, the rate constant is, we decided to use a rate constant of 1.902 per day. So basically it's going to be 1.902, and then the saturation oxygen level is going to be 9.092 milligrams per liter. So it's going to be 9.092. Okay, so that takes care of our aeration. There was a reason why I first did basically add the constituents and I add the source, because now actually my work is going to be easier. When I create my open channel, I can do it in one shot. I can actually create all the blocks in one shot, rather than, you know, creating the block and then applying aeration to every one of them one by one. Okay, so now we are done with implementing the reaction network and the aeration and so on. So let's now create the channel segments. So basically, what in order to do that, what I'm going to do is that I'm going to use this feature of create 2D array. So I'm going to go to the Add Objects menu, and then I'm going to pick Create 2D Array. So then what you will see is this is the first page that you see. So first thing we have to do is that we have to select our block type and also the link type. So what component we're going to use to link the blocks that we're going to create. So for the block type, I'm going to use trapezoidal channel segment. For the link type, I'm going to use link from a channel segment to another. As I said, basically I'm going to discretize my channel segment into 20 elements. So I'm going to type 20 for the number of grid cells in horizontal direction. I'm going to leave the number of grid cells in vertical direction to be 1 because my model is going to be one-dimensional. So then I'm going to click Next. So here we need to enter some properties for that will be applied to each of the elements that will be created. The first one is, it says BOD concentration, so that's going to be our initial condition, initial BOD concentration essentially. I didn't really indicate what number I was basically going to use in the diagram that I showed you at the beginning of the video. And it really doesn't matter because I'm going to actually look at the steady state solution at the end. So the effect of the initial condition will be, will go away. So basically I'm just going to enter a number. So I'm going to enter 15 here. There's no external mass flow time series for the BOD. There's no external source. There's no inflow concentration. For the DO, I'm just going to use number 5 for 5 milligrams per liter for the initial concentration. For DO, I'm going to have an external source, so that's going to be the aeration. So basically what I'm going to do is that I'm going to just, click here, and there's a drop-down menu, and the only option that I have is aeration. That's my only source. And there's no DO inflow concentration. The Manning roughness coefficient, as we said, is going to be 0.35. And then, so the width and height, these are the size that the blocks will be shown on the screen. They have no effect on the model. There are some properties that we're not going to use, so they don't apply to our problem. So there's no area of agricultural land or agricultural withdrawal. The base width, as we said, is going to be 10 meters. So that's the base width. So the base width is going to be 10 meters. The bottom elevation, so it's actually something I wanted to mention. So as you can see, there are 3 columns here for the property. Some properties we have, boxes for in the second column and the third column. Actually, in all numerical properties, we have that. So what that is basically, if you look here, it says horizontal increment and vertical increment. So basically what this says is that when I move in X direction, how much I want the value of of this property to change. So I can actually have something linearly changing along the x-axis, but I'm increment to the next blocks and so forth. So what I do is at the bottom elevation, I'm going to enter 0 here. So what that means is that my upstream block will have a bottom elevation of 0. And then if you remember, I was going to use a slope of 0.0001. And then the length of each of the elements is 1,000 meters because I have a 20 kilometer segment that I'm going to discretize into 20 elements. So each of them will have basically a length of 1,000. So 1,000 times 0.0001 is going to be 0.1. So when I move in X direction, the bottom elevation is going to drop by 0.1 meter for every increment. So what I'm going to do here is that I'm going to enter minus 0.1, minus because the value is going to drop. So minus 0.1 in X direction. And I don't need to enter anything for the the vertical increments because I don't have any vertical increments. My model is one-dimensional. There's no obstacle. The initial water depth, I'm just going to enter something. I'm going to enter 0.5. There's no inflow time series. The segment length is going to be 1,000 meters. This is the name that will be applied to these segments. Of course, a number will be added. So basically, the blocks, when they're created, the first one is going to be called trapezoidal channel segment 1, 2, 3, 4, so forth. But I'm going to make it simple. I'm just going to, just call it segment. And then area of non-agriculture activities and so on I can actually ignore. The side slope is going to be 2. And then I'm going to also do one. So these are the visual X and Y. So these are basically what you see on in the graphical user interface for the blocks. So they have no effect on the process happening in the model. But what I'm going to do is that just to make it more visually appealing, I'm going to let the blocks to drop by 20 pixels or whatever unit that is for every block, so that I can see that the channel is actually sloped, right? So that's what I have. That's all the properties we need. Then I don't know. This is the properties of the links, but the links basically channel segment to channel segment link. It doesn't have any properties, so it's just a name, and I don't know. I can just call it channel link. And then of course I don't have any links in Y to Y direction, so I don't have to worry about this. And then I'm going to type generate. So that's it. So I created the array, and basically I click on each of them, and the properties that I've assigned should be here. Okay. And if I look, for example, at the bottom elevation of where's the bottom? So this is the bottom elevation. The first one, the bottom elevation is going to be 0. If I go to the second one, it's going to be minus 0.1 and so forth. And the last one is going to be minus 1.9. Okay, what next? I need to do 2 things. I need to impose my boundary condition. So basically, I'm going to have a flow going in through the upstream boundary. I have a DO concentration, I have a BOD concentration. In general, these are time series data. Now, the fact that I'm going to use a constant value, I still have to create time series for these things. But they're going to be simple time series data. So basically, in order to provide time series data to OpenHydroQual, I need to create these text files. So you can actually create text files with any text editor that you have. If you use Windows, you can use, I don't know, TextPad or Notepad or Notepad++. I'm using Linux here, so I'm going to use gedit. So here is my gedit. I just basically create a new file. And then what I'm going to do, I'm going to create the flow time series data here. OpenHydroQual, what it does is that it basically interpolates the values. So when something is constant, all I need is to provide 2 points, and then it's going to interpolate the values between those 2 points. And what I'm going to do is that I'm going to run my model for 1 year, for 365 days. So basically what I will do is that I'll say I start from time 0, and the flow rate is going to be 540,000 cubic meters per day. Right, so basically I'm going to say at time 0 the flow is going to be 540,000, and then at time 365, day 365, the flow is also going to be 540,000. And then I can just save this. Let me save it as, I'm going to call it SP flow. So I'm going to call this, I'm going to save this as SP flow. I already had that file, so it's asking me to replace, and I want to replace it. So then let's create another file for the DO concentration at my boundary. So again, at time 0, the value is going to be 7.09 milligrams per liter. So this is going to be 7.09. At time 365, it's going to be 7.09. And then I'm going to save this as SPDO right here. And then I'm going to create another file for BOD. So the value of BOD at my boundary is going to be 16.66. So at time 0 it's going to be 16.66, and at time 365 is also going to be 16.66. And I'm going to save it as SPBOD right there. So now I have the boundary conditions. Okay, so I have the boundary condition. Let me go and apply those boundary conditions. So basically I'm going to go back to my model, and I'm going to pick the most upstream block or element, and I need to apply these three. So first I have this inflow time series, so that's going to be my flow, the flow going to the system. So I'm going to click on this, and then I'm going to use SP flow, so that's going to be the flow. Then I am going to, for the BOD inflow concentration, I'm going to go here, and I'm going to provide the BOD SP BOD. And by the way, you can actually check whether that the files you created are valid, and they basically are what you expect to be. So basically I can just right click on the file name and say plot, and you'll see that the value is constant. It's around 16. I mean, it has to be 16.66, which it seems to be right. And then I'm going to do the same thing for the DO inflow concentration. So I'm going to click here, and I'm going to use SPDO. That's going to be the inflow concentration. And that's it. So we have, I'm going to save my model. So what we have the upstream boundary condition basically set up. Now what I'm going to do is that I want to also apply the downstream boundary condition. So for that, I'm going to use a fixed head boundary. So this is a fixed head boundary. So I'm going to just click on this one. Basically, when I click, it's going to add one, but it's going to go behind my upstream trapezoidal channel. So I'm just going to drag this downstream. The downstream boundary, the head, we said it's going to be minus 1.9 meters. So what I'm going to do is just assign the head value for this fixed head to be minus 1.9. And then all I need to do is to connect these the downstream element to the fixed head. So I'm going to basically, this is the one that I'm going to use. This is the link that I'm going to use. It says, link from a channel segment to a fixed boundary. So this is exactly what I need. So I'm just going to connect my downstream element to the fixed head, and we're all set. Oh yeah, actually one more thing. I said that we're going to run this model for 1 year, for 365 days. So by default, if I run this, it's going to run for only 1 day. In order to change that, I'm going to go to settings, general settings, and then I'm going to change the simulation end time. I had to right click on the value and then insert in numeric format. I'm going to change this to 365. Let's save the model again, and now I'm going to run the model. Saving model outputs. Okay, and done. So basically this is finished. Now let's check some results. So basically, let's pick, I'm gonna look at element 5, 15, 5, 10, 15, and 20, and then look at DO. What we expect is that the oxygen sag curve, we expect the oxygen to go down and then recover back. So basically this is element 5, segment 5. So I'm going to look at DO concentration. So actually it takes some time for it to reach a steady state, but it's actually pretty quick. So I didn't really need to run the model for 365 days. Maybe 1 day was enough. But anyways, so that's the DO concentration, element 5. Let's also check element 10. So this is our element 10. Let's look at the DO concentration. I'm going to actually copy this to compare it with the DO concentration in element in element 5. Okay, here is the element 5, so I'm going to copy this, I'm going to paste it here. So as you can see, it goes down. And then element 15, right? So this is element 15. Let's look at the DO concentration here. Again, I'm going to copy this and paste it on this panel, and I'm going to close this. Let's go to 10, element 10, which is our downstream element, and look at the DO concentration. I'm going to copy and paste it here. So and then let me change the color so that it's more clear. So what I'm going to do is that I'm going to make you know, element 10 color, I'm going to make it blue. Element 15, I'm going to make it green, and then element 20, I'm going to make this, let's say, black. So as you can see, the concentration actually goes down. Element 10, it goes down. I have the lowest number, and then it starts recovering back. You can also look at the BOD concentration. So BOD concentration, I expect it to exponentially decreases as I go downstream. So if I look at the upstream boundary, the BOD concentration is around, I don't know, 16. Actually, our inflow concentration was 16.66. This is going to be a little less than that. At element 5, oh, actually this is 6, so 5 is going to be around 12.5, and then the downstream boundary, the BOD concentration is going to reach to something around 6 milligrams per liter or so. Yeah, so this is how we built a Streeter-Phelps model using OpenHydroQual, and thank you for watching. Subscribe to this channel so that, you know, when I post new videos, you can, you know, get notified, and look more for my future videos. Thank you for watching.